In the spring of 1600, the Holy Roman Emperor sat in his palace in Prague with a problem that was keeping him up at night. His astronomers had spent years trying to build the most accurate map of the heavens the world had ever seen. The raw observations were there. The instruments were the finest ever built. But the mathematics required to turn those observations into a working model of the solar system was so punishing, so relentlessly tedious, that progress had nearly ground to a halt. Multiplying 7-digit numbers by hand thousands of times, checking and rechecking every result, it was less like doing science and more like serving a prison sentence. What the astronomers needed was not more data. They needed a faster way to think. What they needed was a tool that did not yet exist. And the man who would need it most was not yet even in Prague. He was traveling toward it on a muddy road, carrying nothing but a suitcase of radical ideas and a desperate need to prove them right. Johannes Kepler had not had an easy life. He was born premature in 1571 in a small German town, the son of a mercenary soldier who abandoned the family and a mother who would later be accused of witchcraft. He was sickly as a child, partially blinded by smallpox, and grew up in a household that was by his own description dysfunctional and volatile. And yet, somehow, he had made it through university on a scholarship, trained as a theologian, and ended up teaching mathematics at a provincial school in Graz. It was there, while drawing a diagram on a chalkboard for his students, that an idea struck him so hard he spent the rest of his life chasing it. Kepler believed the universe was built on a geometric plan. Specifically, he thought the spacing of the 6 known planets could be explained by nesting the 5 Platonic solids: the tetrahedron, cube, octahedron, dodecahedron, and icosahedron, inside one another like Russian dolls, with a planetary sphere fitting between each one. It was a beautiful idea. It was also, ultimately, wrong. But in 1596, it was radical enough to get him noticed, and it led him toward the one man in the world whose data could either confirm or destroy his theory. Tycho Brahe was a Danish nobleman and the greatest observational astronomer who had ever lived. For over 20 years, he had run a state-funded observatory on a Danish island, equipped with instruments of his own design, measuring the positions of the planets with a precision nobody had come close to matching. His data was his empire, and he guarded it accordingly. When political tensions forced him out of Denmark, he relocated to Benátky Castle outside Prague, where Emperor Rudolf II had offered him the title of imperial mathematician. By the time Kepler arrived at the castle in early 1600, Tycho was the most powerful figure in European astronomy. Kepler was a relatively unknown schoolteacher with a geometric fantasy. Tycho gave Kepler a problem to work on, not because he trusted him, but because he was careful not to let any single assistant see too much of his data at once. The problem was Mars. Of all the planets, Mars had given Tycho the most trouble. It moved in complicated loops across the sky. Its speed varied in ways that no existing model could cleanly explain. Tycho had devoted years of measurements to it and still had no satisfying answer. Kepler looked at the problem and, with the confidence of someone who did not yet know what he was dealing with, announced that he would solve it in 8 days. He was wrong. It would take him nearly 8 years. The method he used was essentially brute force. He would guess a set of orbital parameters, run the numbers all the way through to a predicted planetary position, compare that prediction against Tycho's measured values, note the discrepancy, revise his guess, and start again. Each full cycle of this process involved dozens of multiplications and divisions of numbers running to 6 and 7 digits. A single arithmetic error, and Kepler made many, could invalidate an entire chain of work without revealing where things had gone wrong. He would have to trace back through the calculations step by step until he found the mistake. Then, start again. He repeated this cycle 70 times in the first year alone. This was the true crisis of astronomy in the early 17th century. It was not a lack of observations. It was not a shortage of brilliant minds. It was arithmetic. Raw, grinding, unforgiving arithmetic that consumed months of a scientist's working life for results that could be undone by a single misplaced digit. The tool that would change this did not yet exist. But in more than one place and more than one mind, someone was beginning to see the shape of it. The mathematicians of the early 1600s were not without resources. There were techniques available for easing the burden of large calculations, and the most promising of them had roots going back to antiquity. One approach that circulated among mathematicians drew on a property of geometric progressions that had been known since the time of Archimedes. In 1544, a German mathematician named Michael Stiefel laid it out clearly in a book called Arithmetica Integra. Stiefel took the sequence you get by repeatedly multiplying by 2, 1, 2, 4, 8, 16, 32, 64, 128, and above each value he wrote an index number representing its position in the list. He called these index numbers his exposed numbers. Today we call them exponents. The trick was this: if you wanted to multiply 8 by 16, you didn't have to multiply directly. You looked up their exposed numbers, 3 and 4, added them together to get 7, and then looked up which number in the sequence had an exposed number of 7. The answer was 128. Multiplication had become addition. Division worked the same way in reverse. You subtracted exposed numbers instead of adding them. For square roots, you halved the exposed number. For powers, you multiplied it. On paper, this was remarkable. In practice, it was nearly useless for serious scientific work. The problem was the gaps. Stiefel's table only contained exact powers of 2, 1, 2, 4, 8, 16, and so on. If you needed to multiply 41 by 740, neither number appeared anywhere in the table. And as the values grew larger, the gaps between consecutive entries grew wider. The table became less useful precisely where precision mattered most. What astronomers needed was a version of this idea that worked for any two numbers, not just the handful that happened to be exact powers of a convenient base. Until someone solved the spacing problem, the exponent trick remained an elegant curiosity rather than a working tool. But the person who cracked it would hand science something it had never had before, a way to do months of computation in days. Back at Benaki Castle, Kepler's situation was becoming more complicated by the day. He and Tycho were a volatile combination. Tycho was aristocratic, paranoid about his data, and accustomed to running his household like a small feudal court. Kepler was intense, blunt to the point of rudeness when he disagreed with something, and constitutionally incapable of pretending to believe a theory he thought was wrong. They clashed repeatedly in those first months. At one point, Kepler left the castle entirely in a rage, only to return after a tense exchange of letters. But they reached an uneasy equilibrium, and in September of 1600, together they persuaded Emperor Rudolf to fund an enormous new project, a comprehensive set of astronomical tables that would calculate and predict the positions of all known planets and chart over 1,000 stars with greater accuracy than any previous attempt. These would be called the Rudolphine Tables, in honor of the emperor. They were meant to be the defining astronomical resource of the age, useful for navigation, for calendar reform, for horoscopes that governments actually trusted, and for the scientific theories that were beginning to reshape how Europeans understood the cosmos. Less than 2 months after that agreement was signed, Tycho Brahe fell ill. He was 54 years old. The illness came on suddenly and progressed fast. Within days it was clear he was dying. He summoned Kepler to his bedside and urged him to finish the tables. Despite everything, the arguments, the ideological disagreements, the mutual suspicion, Tycho's final wish was that his life's data would be used to produce a work worthy of his 20 years of observation. He died in October 1601. 2 days later, Kepler was appointed imperial mathematician in his place. He took control of Tycho's data over the loud objections of the Brahe family, who wanted the observations kept within the family and used to vindicate Tycho's own cosmological model. Kepler had other plans. He had the data now, and he intended to follow it wherever it led, regardless of whose theory it supported. What it led him to was one of the most consequential moments of stubbornness in the history of science. After years of iterative calculation on the orbit of Mars, Kepler had arrived at a model that came extraordinarily close to matching Tycho's measurements. Extraordinarily close, but not perfect. One of his predicted positions was off from Tycho's observation by 8 arc minutes. 8 arc minutes is a quarter the apparent diameter of the full moon. Any other astronomer working with any other dataset would have called that close enough and moved on. But Tycho's measurements were not like any other dataset. Their precision was documented and verified over 2 decades. Kepler knew with certainty that Tycho did not make 8 arc-minute errors. So instead of rounding down and calling the model finished, Kepler threw the whole thing out. He wrote that these 8 minutes alone would lead the way to the reformation of all of astronomy. He abandoned the assumption, held since ancient Greece and never seriously questioned, that planets moved in circular paths. He tried oval shapes. He tried combinations of circles. He calculated, discarded, and started again. And then, after years of working through the geometry of egg-shaped orbits, he tried something he had long resisted because he assumed the Greeks would have already found it if it were true. He tried ellipses. Everything clicked. Mars moved in an ellipse with the Sun at one of the 2 focal points. A line drawn between the planet and the Sun swept out equal areas in equal amounts of time, which explained both why Mars moved faster near the Sun and slower far away. These were Kepler's first 2 laws of planetary motion, results of such simplicity and power that they seem almost inevitable in hindsight. But they had cost him 8 years of relentless calculation and more arithmetic than most people do in a lifetime. And the Rudolphine tables, the project Tycho had charged him with finishing on his deathbed, were still nowhere near done. Around this time, Kepler had become friendly with another man who had recently come to Prague in service of the emperor. His name was Jost Bürgi, and he was unlike any other figure in Kepler's orbit. He was not a nobleman or a university academic. He was a clockmaker, but a clockmaker of such extraordinary precision and inventiveness that a previous employer had called him a second Archimedes. He had built clocks accurate enough to be used for astronomical observation, constructed elaborate mechanical globes, and made improvements to an existing calculation technique called prostaphoresis, which used trigonometric identities to convert multiplication into addition. He was a practical genius, and at some point, working quietly and without any apparent urgency to publish, he solved the spacing problem that had made Stifel's exponent table useless. Bürgi's insight was that the gaps in a geometric table became as small as you needed them to be if you chose a base close enough to 1. Instead of multiplying by 2 and getting values that doubled each step, he tried multiplying repeatedly by 1.1. The steps were much smaller, the values were much closer together, and if you went even closer to 1, say 1.0001, the table became fine-grained enough to be genuinely useful for scientific calculation. Here is how it worked in practice. Take a multiplication problem, 41.8 times 740. Neither number appears in Stifel's table, but in Bürgi's finer table, both numbers have corresponding index values, what he called red numbers, while the actual calculated values were his black numbers. You look up the red number for 41.8, look up the red number for 740, and add them. Then you look up what black number corresponds to that sum. That black number is your answer. Multiplication has become addition. The trade-off was volume. The closer your base is to 1, the more entries the table requires to cover a useful range of values. Bürgi calculated that a base of 1,0001 would give him the precision he wanted, but that covering the necessary range would require roughly 23,000 entries, every one of which had to be calculated by hand. He did it anyway. His method was systematic enough that the computation, while enormous, was not conceptually difficult. Each entry was just the previous one multiplied by the same small ratio. He likely completed his tables within a few months of sustained work. What he did not do was publish them. Bürgi finished his tables by around 1610 at the latest, and possibly earlier. He shared them selectively, apparently including with Kepler, but he had no particular interest in putting them before the public. He was a craftsman, not a scholar. Priority and credit were not values he seemed to organize his life around. When he finally did publish in 1620, it was too late. A Scottish nobleman had beaten him into print 6 years earlier, and history had already made up its mind about who deserved the credit. John Napier was not, on the surface, the kind of person you would expect to revolutionize computation. He was a Scottish landowner, a Protestant polemicist, and a man whose neighbours in Edinburgh genuinely suspected him of practicing sorcery. He kept a black rooster as a pet and was known to wander his estate at night. His most celebrated publications before 1614 were theological works arguing, with considerable mathematical ingenuity, that the Pope was the Antichrist, and that the apocalypse would arrive somewhere between 1688 and 1700. He was, in other words, an eccentric, But Napier was also a serious amateur mathematician with a deep awareness of the astronomical community's computational burden. He had been thinking about the multiplication problem for years, and the approach he eventually developed was more conceptually ambitious than anything Bürgi had attempted. Rather than simply constructing a fine-grained table of a geometric series, Napier built his system on a precise physical analogy. Imagine two lines. The first is a line segment of fixed length. Napier chose 10 million units, a number chosen to align with the sine tables astronomers already used. A point moves along this segment, but not at a constant speed. Its velocity at any moment is proportional to the distance it has left to travel. So it starts fast, slows continuously, and asymptotically approaches the far end without ever reaching it. The second line is an infinite ray along which a second point moves at a perfectly constant speed, covering equal distances in equal times. Napier showed that the relationship between these two motions had a remarkable property. Equal ratios on the first line correspond to equal distances on the second. If the point on the first line travels half the remaining distance, the point on the second line always covers the same fixed length, regardless of where it started. This meant that multiplying values on the first line was equivalent to adding distances on the second. Multiplication had become addition. Napier called the distances on the second line his ratio numbers, logarithmi in Latin, logarithms in English. The concept was more powerful than Bürgi's because it was not just a table. It described a continuous relationship between two number systems. Any value, not just those that happened to fall on a pre-calculated list, had a corresponding logarithm. In practice, of course, you still needed a table to look things up. But the underlying mathematics was now a genuine function rather than an approximation built from repeated multiplication. To build his actual table, Napier did use a geometric series as an approximation, repeatedly multiplying by 0.999999, a number just below 1. But to avoid having to calculate 7 million entries, he developed a layered system of landmark values and interpolation that let him build a complete table with far fewer direct calculations. And he tailored the output specifically for astronomers. Instead of listing powers of numbers, his tables gave logarithms of sine values. 1 entry per arc minute from 0 to 90 degrees, 5,400 entries in total. An astronomer could go directly from an angle to its logarithmic sine without any intermediate conversion. The tool was designed for the people who needed it most. Napier had been working on this for 20 years. He published in 1614, at the age of 64, in Failing Health. He said he wanted his work to be common to all and freely available for public use. The response was immediate. The East India Company commissioned an English translation to distribute to its navigators. Astronomers across Europe recognized what they were holding. The age of the logarithm had begun. Kepler got hold of Napier's logarithms around 1617. He was still in the middle of the Rudolphine tables. Emperor Rudolf had been dead for 5 years. The imperial court was perpetually late with his salary, and he had never been able to afford the assistance he needed to share the computational load. He was doing everything himself. When he read Napier's work, his reaction was not the cautious appreciation of a scientist encountering a useful new tool. It was closer to the response of a drowning man who has just been thrown a rope. But logarithms did more for Kepler than simply accelerating his existing calculations. They revealed something he had been looking for his entire career. Since his earliest days as an astronomer, Kepler had been convinced that the solar system was governed by a hidden mathematical harmony, some precise numerical relationship between the planets that reflected the geometric perfection he believed the universe to be built on. He had spent years looking at the data from every conceivable angle without finding it. The signal, if it existed, was buried in the noise of raw numbers. He knew that planets farther from the sun took longer to complete their orbits. He knew they also moved more slowly. He suspected these two facts were connected, that the sun exerted some kind of weakening influence with distance that governed both the speed and the period of each planet's motion. But the precise mathematical form of that relationship had eluded him. When he took the logarithms of the planet's orbital periods and their distances from the sun and plotted them against each other, the relationship appeared instantly, a straight line. The square of a planet's orbital period is proportional to the cube of the semi-major axis of its orbit. It held for every planet. without exception. This was Kepler's third law of planetary motion, published in 1619. It is still used today in the calculation of satellite orbits. Kepler was so overwhelmed by the power of what Napier had given him that he immediately wrote to Scotland to thank him personally and dedicated one of his books to him. He did not yet know that Napier had been dead for 2 years. Almost as soon as Napier published, an English mathematician named Henry Briggs identified a flaw. Napier's logarithms were powerful but slightly awkward to use. The scaling step required to keep values within the table's bounds was fiddly, and the way Napier had constructed the system meant that the logarithm of 10 was not a round number, a constant inconvenience for anyone doing decimal arithmetic. Briggs proposed a fix, set the logarithm of 1 equal to 0 and the logarithm of 10 equal to 1. Under this convention, every time a number was multiplied by 10, its logarithm simply increased by 1. The scaling problem dissolved. The system aligned perfectly with decimal notation. Briggs travelled to Edinburgh to propose this to Napier directly, and Napier, though too ill to do the work himself, immediately agreed it was the right approach. Briggs spent the next 8 years recalculating the tables from scratch, using the new base. What he produced, base 10 logarithms, the common logarithm, became the standard form used by every scientist, navigator, and mathematician for the next 3.5 centuries. Even today, when someone says log without specifying a base, in most practical contexts they mean Briggs's version. With Napier's logarithms in hand and Briggs's refinements on the way, Kepler finally had what he needed to push the Rudolphine tables to completion. It took 4 more years of work after that, delayed by war, by money troubles, by the demands of defending his mother against witchcraft charges in a trial that consumed years of his attention. But in 1627, 26 years after Tycho Brahe had pressed the project into his hands on his deathbed, the Rudolphine tables were published. They were 30 times more accurate than any previous planetary tables. They could be used to calculate planetary positions all the way back to 4,000 years before the Common Era and forward into the indefinite future. The frontispiece Kepler commissioned for the book depicted Tycho standing at the center of a great columned structure in conversation with Copernicus. On the roof stood 6 allegorical figures representing the pillars of his astronomy. One of them represented logarithms, and at the base of the structure, alone working by candlelight, was Kepler himself. It was the most accurate astronomical resource in the world, and it remained the defining reference for navigators and astronomers for more than a century. The Rudolphine tables eventually gave way to newer and more precise instruments, but the logarithms that had made them possible endured for far longer than anyone in 1627 could have anticipated. For the next 350 years, every working scientist used them. Newton used logarithm tables when developing his theory of gravitation. So did the engineers who designed the bridges and railways of the Industrial Revolution. So did Einstein. So did the teams of human computers, many of them women, who calculated artillery trajectories in 2 world wars. So did the physicists and engineers at Los Alamos. And so did the engineers at NASA who put a human being on the moon. The physical embodiment of the logarithm, the slide rule, a mechanical device that performed multiplication and division by adding and subtracting logarithmic distances, was the standard scientific calculator from the 17th century until 1972, when the first handheld electronic calculator made it obsolete overnight. But even that was not quite the end of the story. The algorithms hardwired into those first electronic calculators to compute transcendental functions, the mathematical routines running invisibly beneath every button press, were direct descendants of the methods Briggs had used to calculate his base 10 logarithm tables 350 years earlier. Napier and Briggs had the last word even in the machine that replaced them, and it had all begun with a young astronomer on a muddy road to Prague, carrying a suitcase full of ideas about planetary geometry and an 8-day bet he was about to lose very badly. The math he needed did not exist yet, but the need was real, and when the tool finally arrived, it did not just help him calculate faster. It showed him the shape of the solar system itself, a harmony hidden in the numbers all along, waiting for someone desperate enough to find it.